Okay, so today we are looking for a turbulent flow analysis or else turbulent model. So in the previous cases we also studied about the flow of the fluent, but we only use the condition that is called a laminar. Okay, so we already analyzed a tubed session. So in that session also we apply turbulence, viscosity as a laminar condition. Okay, so you know that what is the difference between the laminar and turbulent. So a laminar is the fluent flows in a regular manner, so there is no disturbance at all. Okay, so the flows look like this. So if it is a turbulence, usually 90% or most of the cases the fluent has some turbulence. So due to the increased velocity and pressures. Okay. So the best example for the laminar flow is our blood. Okay. So the blood is actually flows in a laminar way. Okay. So whenever the aircraft which is having that aerodynamic analysis, the air is hits on a turbulent model. So it should be like there should be some twistings and changes like this. Okay, so what we are looking for in this analysis is what happened when a fluid flows inside a pipe station, so whether it may be a water or air, what will be the velocity and pressure drop nearby the wall. So especially the fluid is a turbulent flow, in the turbulent flow. So in laminar cases and in turbulent cases, the pressure and velocity changes will be much more differ. So when I try to draw a model, a graphical images like this. So usually in the laminar flow, it should be like this. So what does it means? Like at the center, there will be a maximum velocity. So in any cases, at the center of the axial direction, the fluid flows in a high velocity. Okay, so towards the wall, due to the friction, the velocity maybe decreases, the pressure may be increased. So the velocity and pressure is vice versa, directly proportional to each other. So it should be look like this. So we have a maximum velocity at this point at the center and having a minimum velocity at the nearby the wall region. Okay, so in our cases this is the two wall regions. Okay, so let's consider if it is a turbulent flow. So I am showing that this is for laminar condition. If it is a turbulent condition, what happened? You'll get the same graph, but not exactly like that. So you only have a bend like this. Not a too curvy bend. Okay, in the previous cases we'll have a bend like this, right? So we don't need to have that due to the turbulence. Okay, so due to the turbulence, the velocity is actually more or less similar to in this all cases. Okay, but although if it is very closer to the wall, the velocity maybe drops. Okay, so we'll clearly analyzing this problem. Once we get solved this problem, you'll get the difference between the two things. Okay, so we will find the y plus value, y plus wall value in terms of graphs. So we already explained this y plus wall factor in that species problem also. So let's solve this problem and we'll try to find out or figure out that velocity and pressure drop nearby the wall. Okay, so I don't yet give any boundary conditions at all. So I only shows the diameter value of the piped section, and it's having a velocity, that is inlet velocity. So this is act as an inlet and this is act as an outlet, and we have some distance at all. So we will design this model by using design modular, and in this case also we can solve the problem by using symmetrical condition. Okay, so we can only model the half of the session like this. We can only model the sessions only. half of the session. And we can revolve, and we can assume this as a center line. So this center line has this edge. So this model can be rotated in 360. And it's like an axisymmetric problem. It's not a symmetric, axisymmetric. So it can rotate about this axis at a degree of 360. Okay. So we don't yet need to design the entire thing. We can only design the half of the session. So then the distance may be roughly that is equal to 0.1. So the total distance is 0.1, I mean 0.2. So we can create a surface for a design, I mean for the value of 0.1. Okay. So first I will drag and drop the Fluent flow. So the entire session we only working on the Fluent, and double tap on the design modular, I mean geometry. So by default design modular will be get started. So if you want to define this problem, so I want to be only working on 2D, probably you can first define that also. So just right click and you may have an option to choose the properties. So just click on the properties, an additional tab will be opened here. So by using this tab, you can say that I'm only working on that 2D, but right click, properties, see. You may have an option that is analysis type is right now set to 3D. You can choose from 2D, or else when you try to open the Fluent, it always asks, so whether you want to solve the problem in 2D or 3D, you can choose 2D. So right now I am choosing 2D here itself, and open the design modular. The first thing you need to do here is change the unit system. Okay, so by default we only working on meters, because I just draw the model. Okay, so I don't need to give any dimensions at all. So that is 0.2 meters, not mm. Okay, so I don't need to change the units, but just make sure it's set to meters or not. Okay, so once it is settled, just create a random sketch. To get a normal view, just click on here and choose XY, right click and say look at. Go to sketching, I'll draw a random rectangle. Okay, so once it is get drawn, I can make the dimensions. So go to dimensions, mark the vertical and horizontal dimension. So once it is get marked, so I am only interested in the half of the session. So that means the vertical distance is obviously okay, right now the value is having around 18. So if you get, if you say it's 0.1, you get a very minimum length. And the horizontal distance I don't get mentioned over here. So the distance is 8. It's 8 meters. Okay. So I'll say 8 meters. And say look at. For a better view, so probably you can delete the dimension and remark the dimension. Okay, and say look at. Now we'll get a better view. Now we can mark the dimension. Okay, so the horizontal distance is 8 meters and then vertical distance is 0.1 meters. Okay. Now you have to convert the sketch into a surface. You may be familiar with that concept. You have an option that is surface from sketches and choose the sketch. So the best way is you can choose from the design tree, choose the sketch and click on apply. So you don't need to apply any thickness at all, because we are solving the problem by using axisymmetric. So I don't need to want to define any factors at all. Okay. So click on generate. Now the surface will be generated. Okay. So our designing part is completed right now, and just try to close the design modular, or else you can minimize it anyways, and double tap on the meshing to get into that meshing environment. There you can define the mesh and the boundary condition, that is what is inlet and what is outlet, and which act as wall and which act as axis also. So it's good when you, once you created the geometry, probably you can save the geometry for a future reference. But I don't know. I don't want to save the model, because it's a simple model, right? We can easily create that. If it is a complicated model, you can save it for a future references. And choose the surfaces. Just make sure all the properties are correctly assigned. Just check that. Okay, so once it is done, you can try to create a mesh. Okay, so how can I create a mesh? So by default, I just create a default mesh. Just right click and say generate mesh. It will create a mesh like this. Okay, so in this condition, which is my axis? Okay, I just clear the screen. So in this case, this edge, the top edge, is act as a wall, and this edge is act as inlet, and the opposite edge like this act as outlet. And what about this? So this is act as an axis. Okay, so we have the plate like this, so this is axis. So we can revolve around this axis, the entire surfaces, at a degree of 360. Okay. So that means my resultant area. So I'm only interested, it's a turbulent flow, I want to view the result on the nearby the wall. Okay, so nearby the wall. So we need a proper mesh. So how we actually created a proper mesh nearby that airfoil structure, right? So like always, we need to create a proper mesh nearby the wall. Okay, so right now we don't have any splittings over here. So we have so many methods to create a proper mesh. So I'll use one method, that is edge sizing method. Okay. So how can I create that? So just right click on the mesh. So right click and say insert. We'll have an option called sizing. I'll choose this edge and this edge, and click on apply. Now the two edges is selected. So shift the type to number of divisions. I'll give a number of divisions of around maybe 30. So once you give that, we need to also assign that biasing also, but first we'll try to create that mesh, and also I need to apply another edge sizing for this and this, and click on apply. By default it's set to element sizing. I'll choose number of division, and I want divisions of 100. Okay, so in this edge you'll have 100 segments, that is 100 splittings like this, Okay, so and here you only have 30 segments. Okay, right click and say generate mesh. Oh, okay. So you'll end up with a mesh like this. Actually it follows that boundary condition, but not exactly. So here it creates a fine mesh nearby this region and a coarse mesh over here, just because in that sizing the adaptive sizing is not turned on. Just try to turn on that and right click and say generate mesh. Probably we'll end up with another type of meshes. So what I'm going to do here is I just select the edge sizing and change the type of the behavior from soft to hard, it will strictly follow that condition, so what I actually assign. And also I will try to apply a phase mesh for a proper splitting. Right click insert, you'll have an option called phase splitting. You maybe remember that we have used this method in the biasing concept when we do when we learned 2D meshing in Ansys workbench. So what this phase mesh will do is to create which creates a proper mesh. I just apply that. I don't want to change any other factor. Just right click and say generate mesh. Okay, you will have a fine mesh like this. So totally you have a 30 segments and 100 segments in this directions. Okay, but I need a coarse mesh, a fine mesh, coarse mesh nearby the center and fine mesh nearby the wall. Okay, why we need a fine mesh nearby the wall is because the resultant area is nearby my wall. So that is why I need a proper mesh. So the more number of nodes nearby the resultant area, the more number of accuracy we get. So that I can apply a biasing factor. So it's very simple. So just click on the edge sizing. You'll have the option to choose the biasing. I just enable the biasing. You have a linear biasing and then what is that? Bell curve. But I don't want bell curve. I'll choose linear biasing. So it asks you for the biasing factor. Just start with a factor of 5 or 10. Maybe I can use a 10. You maybe notice that now we'll have a more fine mesh nearby the fine segments nearby the wall and a coarse segments towards the axis. Okay, just make sure the other end also having the same thing. I'll just zoomed out and check out this thing. Okay, so in the another end the mesh is actually having the reverse direction. The biasing is in the reverse direction. What you're going to do here is you can just click on the reverse, just click and say apply this edge. I'll get a proper thing like this. Okay, so coarse on this side and fine on this side. So once it is settled, just right click and say generate mesh. Okay, fine. So now we have a fine mesh nearby the wall and having a coarse mesh nearby the axis. Okay. Yep. So hope you will understand what I'm gonna do. Yes. Okay. We successfully created our mesh. Okay. So the next thing is we need to assign the boundary conditions. So that is very, very important. For that, you can just create a named selection. In this case, it's very, very easy. So just right click, just select this edge, make sure you are in the edge selector mode and choose this edge and right click and say create named selection. It's inlet, click on OK and the opposite end just select this edge, choose this edge and right click and say create named selection. We name it as an outlet. And click on OK. Okay. Now we have a two named selection, one is inlet and one is outlet. And this thing, so we know that it's wall, right? Wall. And say OK. And also you need to define the center axis. Just select, right click and create the named selection. Name it as axis. So this keyword is very, very important. Okay, so if you don't include that keywords, the keyword is nothing but I'm talking about that inlet, outlet, wall and axis. These conditions we need to specify in that boundary condition. So when we get into the Fluent environment, right? So just make sure whatever the name you may be given, so the inlet velocity or outlet wall 1 or 2 or 3, so just make sure you should be always use that keyword. Otherwise you need to manually assign everything. It's maybe an complicated process when we are in the Fluent. Okay, so I think we completed our the creation of meshing part and then named selection. Okay, so I just close the meshing environment and try to update the mesh, because once you update the mesh, so the entire data will be transferred to the setup, so otherwise it won't. It will take some time. Okay, so once you get the green color tick mark in the geometry and meshing, you can move on to the next step, that is setup. So just double tap on it. Now the Fluent modulus gets started. So obviously it's a 2D model. We already defined in that properties manager. You don't have the option to shift over from 2D to 3D. And just enable the double precision. You know that if you enable this double precision, your probability of convergence will be increased, and as well as the solving time may be also increases. So it doesn't make any sense. Obviously we need a convergence problem, right? So just enable that precision and get started with Fluent. Okay, so once it is get opened, just try to zoom, and this model, just make sure you have a proper mesh. Just click on check. You can check the volume statistics and phase area statistics, and make sure all the values are in the positive. If you have any negative values, probably your geometry will have some open loops. So you need to go back to that design modeler and make sure the model is correctly modeled or not. Okay. So the next thing you need to do here is to set this thing, that is 2D space. So right now in 2D space, by default it chooses to planar. It's not a planar analysis. Right now we are doing an axisymmetric problem. So I'll choose axisymmetric. And one more option is available below this, that axisymmetric squill. So what does it do is, it revolves the model in this direction, like this. So not this, in this, like a spring. Okay. So in that case we'll use this option, but in our case we only use it axisymmetric. Okay. Like also we use a YAR, so that is why it's a compressible. So we'll go with pressure based one. We don't need to use density based one. And the velocity, it doesn't varies with respect to time, so we stick to steady state. And if you want to add the gravity, you can add the gravity, but in this case I don't want to turn on the gravity at all. Once everything is done, so if you want to change the unit system for any values like length or masses, you can change it from here itself. And I will move on to the model to define the viscous condition. Okay, so in this case there is no temperature or anything is involved in this case, so that is why I don't turn on this energy equation. I just leave as it is, just turned off, and just click on the viscous condition to define the viscous. So as I said before, so our case is, our flow is turbulent flow. Okay, so you don't need to choose laminar at all. For turbulence, so other than that laminar, all the conditions we have sparkler and then K epsilon, K omega, these things are a turbulent flow. But for our convergence, I just follow the values which is having in your PDFs. Okay. So if you give you can also give your own values, but your problem will take some more than 5 to 6 number of iteration to get convergence values. Okay, so to view all the things like how to assign this and then how to view the result, for that we just follow the same thing. When we follow these things, we get a proper convergence factor. So I'll choose k omega, that is equation 2. So once it is chosen, okay, so I'll choose k epsilon. So once it is get selected, either if you want you can use a standard one, or else in some cases we'll use reliables. I mean in which cases we use in upcoming session we'll have a periodic flow, so in that cases also we'll use the reliable. So we have some one PDF also, so in that PDF you'll notice you'll have some recommendations, so in which cases I can use k epsilon, in which case I will go with k omega factors. So I'll share the PDF also. And obviously you need to choose the enhanced wall treatment condition, because my result is only nearby the wall condition, right? So if you choose enhanced wall treatment, you'll get a proper result nearby the wall. Okay, so once it is selected, I don't want to disturb any other things. I'll just leave as it is and say click on OK. So now our viscous model is get assigned. So the next thing is you need to do here is the creation of material. So just double tap on the material. So by default the fluid is air. So just click on that. So I'll change the density to 1 and the viscosity factor to 2 e power minus 0.5. Okay. So once it is get changed, just click on change and create. So it asks you to overwrite. So once it is updated, just click on close. Okay. In our case, our fluid domain is a fluid. Okay, so the one thing we forgot to do is we don't need to assign that surface is a fluid, right? In the design modeler. So whenever you create a surface, just make sure just click on the surface. Right now by default it's set to solid. So I will shift to solid from fluid and say close and right click and say update. So by default the surface is set to solid. If you don't change from here, it won't be included in the Fluent itself. Okay, now the meshes get updated. So in Fluent itself, you'll have an option to update. So do you want to update the mesh changes? Yes, okay. So now it is get updated. Okay. So the remaining condition you don't need to change at all. So okay. So once it is updated, so right now we only working on a single fluid, that is the air. So we need to assign that fluid, right? So just click on the cell zone condition and fluid. This surface body is by default assigned with the air. And so click on apply and close. I don't want to change any at all. And directly we will move on to the boundary condition. So we have so many conditions, that is axis, inlet, like this. So when I click on inlet, by default the velocity inlet is involved. I'll click on edit. So in my condition the velocity may be 1 meter per second. So other than that you will have two factors. So that is turbulent intensity and turbulent viscosity ratio. So also you have a ratio to choose that. So that is you can also define the turbulence rate by the intensity and then hydraulic diameter. Okay, what does it means? So it defines the intensity of the turbulence. Okay. So what does it mean? Turbulence means like the spinning of the fluid we have. So how can we actually calculate this? Is the range of the Reynolds number. Have you aware of that Reynolds number? So the Reynolds number's value is defined by the factor of, once again, so V, D and U. So in our cases, they give the factor that is 10,000. So we know that over 2,400, I mean below this region, we consider it as a laminar flow. Over this condition, we call it as a up to 4,800 range, we call it as a transitional flow. Over the 4,000, we call it as a turbulent flow. So totally you have two things. If you give the factor of 5% turbulence intensity, so you maybe have a low turbulence. I mean, there is no much difference. I mean, much disturbance at all. So if you increases this factor up to between 20 to 35%, give any factor which is between 20 to 35, we call it as a medium turbulence. So over 50 or 60, in between 35, over 35, and then in between 60 to 100, not 100 at all, we around 70 region, we call it as a high turbulence. So based upon the turbulent intensity, you can give the factor. So right now I use 5. And what does it means, hydraulic diameter? So that is my pipe diameter. Okay, so my pipe diameter is 0.2. So I have to give that 0.2. So once it is set, and click on apply. So since even though if it is a symmetrical problem, you have to give it as a whole value, that is diameter value. Don't give the value as 0.1 and close it. So now our inlet conditions is set it, and just click on axis, and by default the type is set to axis. You don't need to worry about that. So if you say any other name like center line, if you name it as a center line, probably you need to change the type to axis from the steps. So by default I give it as axis, so we don't need to change it that. And outlet condition, you can define that outlet condition. Maybe I'll just select outflow. So whatever it is inlet, inlet velocity, that will be goes on outlet. So I'll give the factor of 1. And wall is wall. We don't have any other factors. So if you want to define the frictional coefficients, you can go to edit and specify the shear factors also in x and y, but I don't want to apply. Just close it. Okay. So now we have defined that axis condition, inlet and wall and outlet conditions, everything. Okay. So the next thing is we need to move on to the solutions, that is numerical solutions. Solutions tab, methods. I'll shift over to coupled to simple and choose second order wind up for all the things. So once it is selected, you can directly move on to the initialization process. So it's better to be with hybridized initialization and click on initialize. So now you get 10 values. Once it is selected, and go to calculation, and maybe you can give an iteration factor of 300 or anything. Okay, so I'll give a factor of 300. Okay, so you can set to 700. Maybe it may take higher iteration factor, and click on calculate. So once you click on calculate, the problem will get iterated. Okay, so the solution is actually converged at 93. Even though if it is not completed or converged, you may get this message, that is your problem, your solution is completed, the calculation completed. So either two things will happen. One is the problem will converge at some values like 93 or 193 or 293 something, or else the entire iteration process will be completed. So it will solve the problems for 700 steps. So that I just close the design modeler. Fluent. Just click on results.